The last case is ANOVA, and I'm going to pick the mouse diet case this time. If I double click on the mouse diet file, and this will open up IBM SPSS. So here's how long your mouse lives. Here's its diet. There are 4 different diets. Oh, 6 different diets they did. Now, remember what I said about the F-test, because the F-test is going to appear again. Now, this time, it's vaguely useful, but I'm still not overly convinced. Anyway, now I've got 6 different groups of mice, and I want to know, is there a difference in the mean weight between the different groups of mice? Mean lifetime. So there was an idea that if you restrict the calories of people, they live longer. So potentially, this is why human life expectancy has gone up, particularly in Western Europe, because lots of people starved during their childhood because of the Second World War. So potentially, all of those that are born after the Second World War might not live as long as their parents, because they've not had a period of scarcity of food. So the boomers might not live as long as their parents. We don't know yet. We'll find that out in the future. I know from my family that's partially true. My dad died before my grandma did. But that's just anecdote. It's not statistics. So what we want to do is compare the means for more than 2 groups. I've got my groups defined by diet from 1 to 6, and I've got my lifetimes in days, probably, or 35.5 days. Okay. Actually, it might be weeks. I don't know. How long do mice live for? Probably quite sick mice. Let's say it's weeks. I want to do compare means. I've got more than 2 samples, so I can't do independent samples t-test. I have to do this other thing, which is an example of what we call one-way analysis of variance. Why it's called that and everything else is explained in the slides. Let's just click on the button. What's the dependent list? Lifetime. What is the particular factor? Is which kind of diets they have. Now, if I go to view for value labels, the diets are called NP, NN, whatever it is, low protein, NR50, and RR50, and NR40. Now, they have to be converted to numerical things because SPSS will not allow this factor to have characters in it. This is a new feature brought in by SPSS, which I didn't enjoy finding out that they put in halfway through teaching with my old files that suddenly stopped working. This actually was a PC and Mac version, so IBM managed to break SPSS examples, and that sort of annoyed me until I changed all my files to the new format. But anyway, you need to have, if you're doing ANOVA, your factor to be numerical. Let's not worry about contrasts ever, and I won't worry about post hoc at the minute. I'll just run ANOVA. So I press OK. Done. That's done an ANOVA. So the things you're looking at here are, this is your F statistic again. So the F is a very large number. It's 57.104, and the significance of it is 0. So this is saying it's less than 0.0005. So it's definitely less than 0.05. So there's a highly significant difference between the life expectancies of the mice on different diets. Now this is where I go, and so what? I've got 6 different diets. I now know that there's some differences between those 6 diets. Is that at all interesting or important for me to know? Have I advanced science one jot by knowing that piece of information at all? Exactly. Waste of time. But you have to do it. If you get this kind of data and you just go to the next step, immediately they will reject your paper. You have to do the F test. You have to do your Fisher's test, even though I think it is not very useful in the slightest. So what I could have done before I did all this business is I could have actually sort of doing a chart. So what I could do is do some box plots. So let's do a box plot here, and let's have lifetime as the y-axis and diet as the x-axis, and then go OK. And this would show me that the NP group, they have a much shorter lifetime than all these which are on the restricted diets or the low protein groups. So I can see there's practically no difference between these 4 diets, but there are differences between these 4 diets and these other 2 diets, and the worst is the NP diet in terms of life expectancy. So now, because I've looked at it graphically, I've got a better idea about what the differences should be. Now, when I was doing the compare means one way ANOVA, I ignored this box on the side that says post hoc. So post hoc is the worst kind of statistics you do. Remember when we were talking about the t-test data and the serials, I said, why did I pick this particular question? So that's the problem. What people have a tendency to do in science is they collect loads and loads and loads of data and results. They do lots and lots and lots of different t-tests until they find one of them that gives them a significant result, and then they decide that's what their paper's about. This is called post hoc statistics. And for a statistician, you're using what we call posterior knowledge after you've done the experiment, and it's called talking out of your posterior. It's bad. It's a really, really bad way of doing science. So don't. So your problem is that, first thing, you're going to do lots of t-tests. You're going to compare group 1 to group 2, group 1 to group 3, group 1 to group 4, group 1 to group 5, group 1 to group 6, and group 2 to group 3, groups 2 to group 4, group 2 to group 5, group 2 to group 6. And you're going to keep going on doing all of these different tests. Now, if you remember, well, the threshold that I've picked for my hypothesis testing is a 0.05. It means a 5% chance of saying there is a difference when there isn't one. That's 1 in 20. So if I do enough tests, I do more than 20 tests, one of them, by chance, will show to be significant when it isn't. So what you have to do is something called multi-test correction. So once you click on one way ANOVA and you click on post hoc comparisons, it gives you a choice of all these different ways you can do corrections. Now the simplest is Bonferroni. You simply divide the 0.05 amongst each of the different tests. So if I do 20 tests, I divide the 0.05 by 20, so that across those 20 tests, I get a probability of getting it wrong of 0.5 in total. Now, there are lots of other ways of doing it. There's Sidak, Schiefer, Tukey, and there's ones when you don't have equal variances. There's all sorts of things you can do. So if I just click on Bonferroni, Sidak, and Schiefer, Schiefer should be good because he wrote the book on ANOVA. The textbook's called Schiefer. Let's continue and go OK. I still get exactly the same table that I got before, the ANOVA table with the F statistic and that. But then what I do for each of the different correction methods is I get comparison. So this is NP against the other 5 diets. This is NN against the other 5 diets. So now you go across, you see the mean differences between the 2 groups. You see the standard error of the differences for the 2 groups. And you see the p-value for the difference between the 2 groups, as well as the upper and lower bounds of the confidence interval. In this case, the confidence interval is always negative, but there is a difference between NP and N over N5. And you can see that in the p-value being less than 0.05. So to be honest, NP is different to all of them. N over N5 is different to all of them. The low pro is different to NP and N over N85, but it's not significantly different to the NR50 and the NR50, but it is different to the NR40. So this table gives you all those differences. Notice that the values here, these are for Schieffer and their particular p-values. For Bonferroni, which is the strictest, you've got a different value. And for Sidak, you've got the same as the Bonferroni, but they don't always come out as even. Each of the different correction methods is going to give you a different set of scores. This is another thing that you must not do, which is pick 3 methods like this and then selectively pick the method that gives you the answer that you wanted to write in your paper. Because you go, oh, Bonferroni found that it wasn't significant. If I use this other method, it is significant. I'll use the other method. No, 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 no. Because you're likely to find that when people try to reproduce your experiment, they find it's not significant. You just happen to have a sample where it was on the border of significant. This is why people do bad science. Don't worry about homogeneous subsets. Those are all the post hoc tests.